Now we will solve our second internal paper, which was an MCQ paper. So, so let us do our first question. Which of the following interpolation technique is used to find the value of a function at a point lying outside the known data point? So see, its answer should be D, Lagrange's theorem, because if we see to the Lagrange's theorems, its formula is summation I from I equals to 1 to n bracket pi j equals to 1 to n x minus xj upon xi minus xj multiplied by I. So let us understand this formula more clearly by solving one question. See, we have x and y. We have given some data points like at x equals to 5, value of fx is 12. So in such a way, data is given, and we have to find the value of y at value x equals to 10, right? So what we will do is use this formula, that is x minus x x of j, that is 1. So it will be 1, 2, 3 and 0, right? So x minus x1, x minus x2, x minus x3 upon xi minus xj. Here I is what? 0. So x0 minus x1, x0 x0 minus x1, x0 minus x2 into x of 5, right? Similarly, we have done with this, this and this, and after solving this whole equation, we will get what? Value of 14.666, right? But if we want to find the value, let's say x equals to 12, we can also solve at value of x equals to 12 using this formula only. Just in place of x, put the value of 12, and we will find the value of a function outside the data point. So its answer will be D, Lagrange's theorem. Let us proceed to our second question, which is which of the following is not a disadvantage of Newton forward interpolation? So if we look carefully, we have to find which is not a disadvantage. Means it should be advantage, right? So first option A is it cannot be used for large value of n. So it's a disadvantage. So it cannot be true. It cannot be a correct answer. Sorry. It requires equally spaced data points. This point is true, but it's one of a disadvantage of Newton forward interpolation, right? It is sensitive to errors in a data points. Yep, that is also true because in approximing the terms, it could lead to a wrong answer. So it is also a disadvantage. It is computationally intensive. Yep, it is true. To understand the meaning of computationally intensive, it means computationally intensive is a term that applies to any computing application that requires multiple computational resources such as grinding computer, right? It means it requires multiple data so that we could find the correct answer more precisely. So it is an advantage of Newton forward interpolation. So D, right? D is a correct answer. Now let us see the third question of our test, that is which of the following interpolation technique is used to find value of a function at a point lying before the data point. So it should be, we have to find lying before the known data point. It should be Newton backward interpolation. In Newton forward, we find the point lying after the known data point, and Newton backward interpolation, we find the data which is before the known data point, right? So what? So let us proceed to our fourth question. Which of the following interpolation techniques uses a polynomial of degree n minus 1 to interpolate n data points? So it should be D, Lagrange's interpolation. Why? Let us see the Lagrange's interpolation formula. So this is Newton Lagrange's interpolation formula. So in this example, you can see we have four data points, right? 1, 2, 3, 4. And if we see this equation here, right here, so we can clearly see that if we solve this equation, it will be of which order? 3 order, right? Because all these terms are in multiplication and x into x into x will be 3. So highest degree would be 3, right? And we have 4 data points. So if we have n data points, Lagrange's interpolation gives n minus 1 polynomial to solve the equation. So it should be D, Lagrange's interpolation. Let us proceed to question number 5. Question number 5 says, which of the following is not a disadvantage of Newton backward interpolation? Option A, it requires equally spaced data points. It is a disadvantage. It is sensitive to error in the data points. It is also in disadvantages, and we have to find which is not a disadvantage, right? It cannot be used for large values of n. It is also in one disadvantage of Newton backward interpolation. So answer should be D. It is computationally intensive. Let us proceed to question number 8. Which of the following is a correct formula for first dividend difference in Newton dividend difference interpolation? Option A is f of xi equals to f of xi. No, this cannot be. F of xi equals to f of xi plus 1 minus f of xi. No. So let us see first the what is the formula. The formula is f of x0 comma x1, that is f of x minus f of x0 upon x minus x0, right? So it should be option number D, right? Xi minus x of I minus 1 x of I minus x of I minus 1. Yep, this is true. It cannot be C because here it is x of I plus 1. So it has to find the one digit mode like x of 5 minus x of 4, and it could cause an error. So answer will be option B. So let us proceed to the question number 9, which is what is the basic difference between the Newton forward and backward interpolation methods? So option A is Newton forward interpolation uses forward differences, where backward interpolation uses backward while Newton forward. So for this, we should see the formula first. So here are the formulas for Newton forward and Newton backward interpolation. In Newton forward interpolation, we use what? Forward difference operator, right? Here you can see it. And in Newton backward, we use nebula, which is Newton backward interpolation, Newton backward operator, right? So what will be the correct option? Forward uses forward difference, right? And backward uses backward difference, right? So answer will be A. Let us proceed to question number 10. In Newton dividend difference formula, what is the purpose of using higher order differences? To increase the accuracy of the interpolation? Yes, that can be true. To decrease the accuracy of interpolation? No. To make interpolation faster? Nah. D, none of these, none of the above. No, none of the above cannot be because it is looking true. Let us see through a question. See, we have a question like we have given x values 5, 6, 9, 11, and fx values 12, 13, 14, 16. So we have finded the dividend forward using forward difference operator, that is 1, 1 by 3, 1, and we have applied this formula in this question, and we have find the values. So higher degree, higher order differences. So what does higher order differences are? Higher order differences are these terms, right? 1, 1 by 1 by 3 and 1. So in calculation, there is 1, 1 by 3. These calculations are used to give increase the accuracy of our question, right? So answer should be A, to increase the accuracy of the interpolation. let us proceed to question number 19. What is the main difference between the Newton-Cotes formula and Gaussian-Quadratis formula for a numerical integration? Newton-Cotes formula uses equidistant points, whereas Gaussian-Quadratis formula use non-equidistant points. So it should be remembered that Newton-Cotes formula uses equidistant points and quadratic formula use unequal or non-equidistant points, right? So let's see other options as well. Newton-Cotes formula uses non-equidistant points, whereas Gaussian quadratic formula uses equidistant points. No, this is false. Both Newton-Cotes and Gaussian quadratic formula uses the same type of points for integration. No, this is also wrong. So it will be A. Newton-Cotes formula uses equidistant points. So it will be A. And Gaussian quadratic formula uses non-equidistant points. Now see 20th question of our second internal paper. Which of the following is an example of Newton-Cotes formula for numerical integration? Simpson one-third rule, Simpson 3/8 rule, trapezoidal rule, or both A and C? So from Newton-Cotes formula, we can derive both Simpson one-third rule and Simpson 3/8 rule. So answer will be D, both A and C. So if we want to go in a detail, so this is a Newton-Cotes formula, that is I equals to nh summation I equals to 0 to I equals to n y into ci raised to the power n. So here what does this ci raised to the power n means? This is ci raised to the power n, it's a Cotes number which we use, and here li is u minus u0, u minus 1, u minus 2, right? So if we want to find Simpson one-third rule, we put value of n equals to 2 here. So if we put value of n equals to 2 here, it will become 2h summation I equals to 0 to 2 yi ci raised to the power 2, right? So now we will apply this formula and find value of ci. So it will be equals to I equals to 2h y0 c0 square plus y1 c1 raised to the power 2 plus y2 c2 raised to the power 2. We have just expanded this term, right? 0 0 1 1 2 2, right? Now we will go for value of L, Lagrange's number. So for value of Lagrange's number, c0 square will be what? 1 by n integration of 0 to 1 by n. So here n will be what? 2. So 1 by 2 integration 0 to 2 L0 u, right? So here these values will come using formula. Here these values will become, and here this value will come. If we solve this, we will get 1 by 6, 4 by 6, and 1 by 6, and putting these values in the formula here, right, again. So we will get Simpson one-third rule. Similarly, if we put n equals to 3 here, we will get the Simpson 3/8 rule. Okay, that is here Simpson 3/8 rule. So the correct answer will be D. That is, we can use both both A and C in Newton-Cotes formula for integration. Example of Simpson one-third rule and Simpson 3/8 rule is the example of Newton-Cotes formula. So let us proceed to question number 15. Question number 15 says, what is the order of the polynomial used in Newton forward interpolation? So let us see the Newton forward interpolations formula, and it is f of a plus h equals to f of a plus u upon factorial 1 del of fa plus u upon u minus 1 upon factorial 2 del square of fa. So if we find out the nth term of this expression, it will be u into u minus 1 into u minus 2 up to u minus n minus 1, right? Because let's see here, it is what our second term starting from 0 0 first second, so it will be into u minus 1, so here it will be n minus 1 upon factorial n minus 1, right? It is what our first second third term minus 3 minus 1, it is 2 into del n minus 1 of fa, right? So if someone asks you about order, what will be it? It will be this n minus 1. So answer for 15th question will be n minus 1. To question number 16. Which of the following interpolation method uses the concept of interpolation error? Newton forward, Newton backward, Lagrange's, and none of the above. So it should be C, Lagrange's interpolation. Because what do you mean by interpolation error? First we will understand that interpolation error is the difference. Interpolation error is a difference between interpolated value, the value which we have found through interpolation, minus the actual value that we have put directly in the formula, right? And what this interpolation error is used for? Interpolation error is used for finding the accuracy of that interpolation method. If the value is small, it is more accurate, and if the value is big, it is less accurate, right? So what is the concept? Lagrange's interpolation uses the concept of interpolation error to estimate the accuracy of the interpolation. The interpolation error is the difference between the true function and the interpolated function that I have tell you. By computing the interpolation error and the error bounds, we can assess the quality of interpolation and make the informed decision about the number and spacing of interpolation points needed to achieve a desired level of accuracy, right? So it should be C. Proceed to question number 17. Which of the following interpolation method can be used to interpolate a function with complex values? Newton forward, Newton backward, divided differences, Lagrange's. So Newton forward and Newton backward can't be the answer because these two uses forward difference and backward difference operator, right? And calculation of complex values is not possible in forward and backward difference operators, right? In divided difference interpolation, we use the concept of divided differences, right? So its computation is so much higher, so we can't use complex values in even in divided differences operators. So answer will be Lagrange's interpolation. So answer will be D, Lagrange's interpolation. Let us proceed to question number 18. What is the drawbacks of using a higher order differences in Newton divided difference interpolation? Higher computational complexity, decreased accuracy. This is not kind of drawback. What is degree of higher degree of polynomial approximation? Not so. None of the above. So answer will be A. Higher computational complexity is a drawback of a higher order differences because its values will be complex, and to solve that it will take more time. So it is one of the drawback of Newton divided difference interpolation. Let us solve the second paper of our second internal test, which was also an MCQ based paper. So our first question is, which of the following is an example of Gaussian quadratic formula for numerical integration? A. Trapezoidal rule, Simpson one-third rule, Simpson three-eighth rule, and Gauss-Legendre quadratic. So its answer will be D, because from numerical integration we derive this formula first, and by putting the value of n equals to 1, 2, 3, we find trapezoidal formula We find trapezoidal formula, Simpson one-third rule, and Simpson 3/8 rule from Gauss legendary quadratic formula, right? Here we can see in this image how we have derived it. So let us consider a function fx which we have to integrate from a to b. So let us take x equals to a plus hu. So what will be dx? Dx will be h du, right? So if we find the points, it will be 0, and here it will be h, right? So what would integration would become? I will become h integration 0 to h f of a plus hu du, right? Now we will expand it by Taylor's theorem. As we know Taylor's theorem, this function will become I equals to h integration 0 to h fa plus u upon factorial 1 forward difference of operator fa plus u into u minus 1 upon factorial 2 del square fa, and so on. Now what we can do is we can integrate all of these terms. So fa will become ufa, u upon factorial 1 will become u square upon 2. Similarly, these terms will become this, and these terms will become these, right? So now we can replace u by n. So I will become h n fa plus n square del fa, and so on. So quadratic Legendre formula, from these we can uh, take n common. So our final formula will look like this. That is I equals to nh fa plus n upon 2 del fa plus 1 by 2 n square upon 3 minus n by 2 del square fa, and so on. Now from here, if we want to find the value of let us say Simpson one-third rule or trapezoidal rule. For trapezoidal rule, we will put n equals to 1. For Simpson one-third rule, we will put n equals to 2. For Simpson 3 by 8 rule, we will put n equals to 3, and we will get this formula, right? So which of the following is a Gaussian quadratic formula for numerical integration? It will be Gaussian legendary formula. Now let us see the second question. Which of the following is true regarding the weights and abscissa used in Gaussian quadratic formula? The weights and abscissas are equal in number. Yes, this is true, because in a Gaussian quadratic formula we divide it in terms of a plus hu, right? So each and every term gets this number. So weights and abscissa are equal in number. This is true. The rest of the formula are weights and abscissa are not equal in number. No, this is not. The weight and abscissa are the same for all orders of formula. No, these values can change, right? So the weights and abscissa are equal in number. This is true. Let us solve question number 3. What is the accuracy for Simpson 382? So first of all, we need to understand what is accuracy. Accuracy means the highest degree order polynomial Simpson 3A tool can solve, and as we know, it can solve maximum of degree 3 polynomial. It can solve polynomial of maximum 3 degree, so it will be C3. Here we can see it as well. When we want a Simpson 3A tool from quadratic formula, we put n equals to 3 to generate this formula. So it will be 3h fa plus 3 by 2 del fa plus 3 minus 3 by 2, and if we solve this, we will get this formula 3h by 8 y0 plus cy1 plus cy2 plus y3, and for more terms it will be like this, and if we add all we will get this general formula I equals to 3h by 8 y0 plus yn plus 3 y1 y2 y4 y5 y7 y8, that is yn minus 2 plus n minus 1 terms, and all the odd terms multiplied by 2, all the multiple of 3 multiplied by 2, right? So its answer would be 3. Let us solve the question number 4. Which of the following is an example of composite integration method? A. Trapezoidal rule, B. Simpson-Wurter rule, Gauss-Legendre quadrature, or both A and B. So what is composite integration rule? Let us see that. The composite integration method is also known as numerical integration or approximation method. It is a numerical technique used to approximate the definite integral for a function over a given interval. The method involves dividing the integration interval into small subsequences and approximating the integrals over each subinterval using subinterval formula. The result of these approximations are combined to obtain approximation of the total integral over the entire range. Its examples are trapezoidal rules, Simpson rules, and midpoint rules. These methods are widely used in numerical analysis and computational science integration that are difficult or impossible to evaluate analytically. So what we have asked, which of the following is an example of composite integration method? So it will be both A and B's, trapezoidal rule and Simpson-Wurter rule. Let us solve question number 5. What is the drawback of using higher order Newton-Cotes formula for numerical integration? A. They are less accurate than low order formulas. They require more function evaluation. They are not applicable to non-smooth functions, and D. None of the above. So in Newton-Cotes formula, abscissas are divided equally, right? So if abscissas are divided equally, so the higher order function takes more abscissas and their calculation becomes more tougher. So its answer should be they require more function evaluation. In higher order we require more function evaluation because they take more abscissas and it gets difficult to solve, so they require more function evaluation. So answer would be B. To question number 6. Which of the following is true regarding the abscissa used in Gauss-Legendre quadrature? They are equidistant, they are non-equidistant, they are dependent on the order of the formula, none of the above. So like a Gauss quadrature formula, Gauss quadrature formula they are also equidistant. So answer will be A. They are equidistant. Let us proceed to question number 7. Which of the following is an example of open Newton-Cotes formula for numerical integration? Trapezoidal rule, Simpson-Wurter rule, Simpson-Triet rule, both B and C. So this question is repeated from previous question. I think it was last question paper, question number 20. So it has been repeated here. So you can see there, or I am explaining in brief here as well. So this is our formula for Newton-Cotes, that is I equals to nh summation I equals to 0 to n yi ci raised to the power n, where this ci raised to the power n is Cotes number and it can be expressed as 1 by n integration 0 to n li u du, right? And what is li here? Li is the Lagrange's interpolation, which can be expressed like this. Okay, so for Simpson-Wurter rule we put n equals to 2 in this formula and we solve this. So 2h summation I equals to 0 to 2 yi ci square. Now we will find what ci square's values. So ci is 0, we will find c0, c1, c2. So c0 would be what, u minus 1, u minus 2 upon 0 minus 1 upon 0 minus 2. Similarly, we will find c1, c2, right, and we will put the values 0 to 2, 0 to 2, 0 to 2 here, and we will solve this, and we will get what values, 1 by 6, 4 by 6, 1 by 6, and we will put these value in this term, and we will get our Simpson one-third formula, right? Now we could apply same these methods for Simpson 3a2. Just put n equals to 3 and solve, and we will get Simpson 3a2. So yeah, it will be both bn's. What is forward difference operator? It approximates the derivative of a function using the values of the function at two neighboring points. It approximates the derivative of a function using the values of a function at three neighboring points, or four neighboring points, or none of the above. So let us write the forward difference operator. So forward difference operator is what? Fx equals to f of x plus h minus fx, right? So it works on two neighboring points, right? As we could see, x plus h minus fx. So it works on two neighboring points. The answer would be what? Two neighboring points, that is A. So 8 answer would be A. Let us proceed to question number 9. What is backward difference operator? It approximates the derivative of function using the value of a function at two neighboring points, three neighboring points, four neighboring points, and none of the above. So let us write the backward difference operator, that is nebula fx equals to fx minus f of x minus x, right? So as we could see, it is working on two neighboring points. So answer should be A. It approximates the derivative of function at the two neighboring points. So answer would be A. Let us proceed to question number 10. What is the divided difference operator? It is used to approximate the derivative of function at a given point. It is used to interpolate a function at a given point. It is used to approximate derivative of a function using the values of a function at multiple neighbor points, or D, none of the above. So let us see what is divided difference operator. So divided difference operator is this, that is f of x1 comma f2 equals to f of f2 minus x1 upon x2 minus x1, and for this it would f of x3 comma f2 x2 minus f of x2 minus x1 upon x3 minus x2. So it is nothing but option number C. It is used to approximate the derivative of a function using the values of a function at multiple neighbor points. As you can see, these are the multiple neighbor points which we are using in divided difference operator. So answer would be C. Let us proceed to question number 11. What is shift operator? It shifts the values of a function to left or right. It approximates the derivative of a function using the values of the function at a multiple neighboring points. It is used to interpolate a function at a given point, and the none of the above. So what is shift operator? Shift operator means e raised to the power n fx can be written as f of x plus nx, right? So what does it do? It shifts the value of a function right or left. So option A will be correct. Let us proceed to question number 12. What is the order or accuracy of Simpson one-third rule? So accuracy means up to which highest degree the polynomial can be integrated. So in Simpson's one-third rule, it will be 2, because let's see with quadratic formula. From quadratic formula, if we want to derive Simpson one-third rule, we put the value of n equals to 2, right? So that we could find the value of Simpson one-third formula. So when we put 2 in this formula, we will get 2h equals to fa plus del fa plus 1 by 2 4 by 3 minus 1 upon del square f. And when we simplify it and add all the terms, we will get I equals to h by 3 y0 plus yn plus 4 times of odd terms plus 2 times of even terms. So answer will be 2. Let us proceed to question number 13. Which of the following numerical integration method is based on the use of forward difference operator? Trapezoidal, Simpson one-third rule, none of the above. So let us see the formulas of all these terms. So in trapezoidal formula, you can see we are not using forward difference operator. So trapezoidal is not the answer. Simpson one-third rule as well, we are not using a forward difference. And in midpoint rule, we are also not using forward difference operators. So answer will be D, none of the above. Let us proceed to question number 14. Which of the following numerical integration method is based on the use of backward difference operator? Trapezoidal, Simpson, or midpoint rule, or none of the above? So let us see the formulas for each option. So in trapezoidal rule, we are not using backward difference operator. So trapezoidal rule cannot be answered. In Simpson one-third rule, we are also not using the backward difference operator, so it can't be answered. And in the midpoint rule, we are also not using the backward difference operator, so it also cannot be the answer. So answer will be D, none of the above. So answer will be D. Let us proceed to question number 15. Which of the following numerical integration method is based on a central difference operator? Trapezoidal rule, Simpson rule, midpoint rule. So let us see the formula. So here we are not using midpoint rule, so trapezoidal rule cannot be answered. In Simpson one-third rule, we doesn't use midpoint rule, so it also cannot be the answer. And in midpoint rule, we can clearly see we are not using the midpoint rule, so it also cannot be the answer. So answer will be D, none of the above. Now let us proceed to question number 16. Which of the following numerical interpolation formulas is based on a divided difference operator? So from starting we are studying that it is Newton dividend difference formula, so it will be A. Now let us proceed to question number 17. Which of the following numerical interpolation formulas uses the polynomial interpolation? So yeah, we are studied before that Newton dividend formula uses a dividend formula, while Lagrange's interpolation uses polynomial interpolation. So it will be B. B would be the answer. Let us proceed to question number 18. Which of the following numerical interpolation formulas is used for interpolating a function with both its values and derivative at a given point? So it cannot be Newton dividend formula, it cannot be Lagrange's interpolation formula. It is Hermite interpolation formula. So what is Hermite interpolation formula? It is nothing but the extension of Lagrange's interpolation, where we are given both its values and derivative of that given point, so that we could find more complicated and more complex answers. So it would be C, Hermite interpolation. Thank you. Let us proceed to question number 19. Which of the following is true for a numerical integration methods based on a higher order polynomial? They are more accurate for those based on a lower order polynomial. They are less accurate than those at a lower order polynomial. They are equally accurate as those based on lower order polynomial, none of them. So it should be A. They are more accurate than the lower based on a lower order polynomial, because in lower order polynomial the the calculation is easier, but we cannot find the more accurate answer. So it should be A. They are more accurate than those based on lower order polynomial. Let us proceed to question number 20. Jacobi method is also known as. So Jacobi's method is also known as simultaneous displacement method. It must be remembered that Jacobi's method is also known as simultaneous displacement method. Thank you. So with this question, we have completed both our first and second internal paper solutions. So thank you.